All right, welcome everyone to Flyte's Community Sync. Today is June 11th, and yeah, this is our first time using this format for this meeting. So if you're watching this either from YouTube or LinkedIn, please drop your questions in the chat. We can see your questions, and we'll do our best to try to cover all of them here live. But yeah, probably the main difference between hosting this in Zoom versus a live stream, it's the interaction. And right now it's enabled. You can just drop your questions in the chat. We can see them and we'll do our best to cover them here. All right. We will have this is a two-part meeting today. The first 30 minutes will be dedicated to Tom's presentation, and we are excited for this. And the remaining 30 minutes will be about the Union Serverless platform, a live demo in Q&A that will also help you learn a lot from both sessions. This meeting it's been live streamed and automatically will be available after the event on Union's YouTube channel and also Flyte's YouTube channel, so you can rewatch anytime. So with that, welcome again, and I think it's the right moment to introduce Tom. So welcome, Tom, again. Thank you for making it, for spending time preparing this to share with the community. So yeah, would you mind briefly introducing yourself, and then we can go with your presentation?
Of course. Thank you, David. So my name is Tom Tuati. I work at Brain.Space, which is a neurotech company. Basically, I'm going to introduce the company, of course, but first of all, I'm a data scientist. I started as a data engineer at the company, and then I, had more interaction with the data as time went by. Yeah, that's pretty much it. My studies are in computer science and psychology, and trying to implement that on a daily basis.
Awesome.
Yes. So let's just dive in. You see the presentation? Yeah? Do you see it? Hold on. Okay. I don't hear anybody. I, hope that it's okay.
Oh, sorry. Can you hear me now?
Yeah, I can hear you.
Yeah,
Yeah.
first time issues. So yeah, we can see your presentation, no problem.
Okay, great.
Sorry.
So this is a brief overview of what we're going to have today. So first of all, we're going to have the introduction of Brain.Space, which is a really cool company. I've been working there for 2 years already. Then a short overview of past in-house solutions for what we do. I'm going to share the typical structure of a Brain.Space workflow, and then some our main workflows and visualizations for exploratory data analysis, machine learning, hyperparam optimization, and what we have coming next. So let's have a sneak peek into the future, okay? User interface, okay? Right? Your AI tool might be excellent at generating the relevant information for you, but what if it could adapt your experience to your current mental state as a unique individual? The lighting, the context, the content itself, everything can be engineered for you, right? And what if there was a robust way you could, as an individual, monitor, analyze, and optimize your own well-being throughout days, weeks, months, and years? Right? That would be pretty cool. I know that for myself. And what if psychological research all around the world was enhanced by a deep model derived from millions of brain scans? That could give a lot of power to the research, right? So our mission at Brain.Space is to pioneer human AI for brain data collection that quantifies emotions, analyzes mental states, and enriches quality of life. Our solution the creation of brain data-based human AI, integrating machine learning with human-like emotional intelligence. We all know these dystopic movies, where there's an AI that talks in a robotic voice and it's completely depleted of emotion or anything like that, right? That's pretty scary. So we want to have, we want to make the AI see the individual, right? So how are we going to do that? We create a brain-based generative AI models, right, through our user-friendly platform, enabling the gathering of brain data to gain valuable insights. These human AI models are integrated into AI-based services and applications offered through a business-to-business subscription model. So on the one side, we have the AI, which can be clear, formed, measurable, right, standardized. It's intelligent and adaptive, right, and it's rational, maybe, right. That's how we aspire it to be. Then we have the human, which can be blurred, layered, subjective, right, emotional, irrational, creative, right. Then we have to bridge the two. It's a big quest to go about, and now we're going to show you, first of all, our data collection tool. So we are using EEG technology, electroencephalography, and this essentially reads electrical signals from the scalp, giving it really good time resolution and frequency resolution. Each person has a different brain, so we need to make something that can scale up easily through hundreds of thousands of people, and can standardize the data because each one has a different brain and a different head, right? So I'm just going to put this short video that shows the headset. It's less than a minute. Then we'll talk about the rest. Okay. Nice. Close that. Okay. So yeah, this is our headgear. It's called Brain Sensei. It automatically adapts to your head. Doesn't need any operator for that, and it's relatively cheap, so it can be distributed for very large quantities of data, right? Just an overview of what we need to do compared to neurolinguistic, large language models, right? So just as a comparison, we are doing the large mental models, right? So normally in a large, like a GPT, right, you need to collect data, engineer the data, label it, using development, right, and train the LLM, right? We need to collect our brain data, right? We need to denoise it because our brain and our movements and the environment is very noisy. It's very hard data to work with. And then we have to standardize it. We all have different brains. We need to standardize it to like a single type of brain, like a universal brain, and create this transformation from the raw data. Then what we need to do is create auto-labeling. We can't just give labeling, subjective labeling, right? You can say, oh, this guy looks like he's pretty happy, or I don't know, he's doing pretty good in this task, so he must be, I don't know, pretty concentrated, right? We need something stronger than that. So what we're using biological sensors from all around the body: heart rate, eye movements, different, galvanic stress response, which is the sweating response when you're stressed. And we are trying to just connect the two and use the world's knowledge of biological sensors to sort of create the labeling for us. And this is a very deep tech topic, so I'm not going to go into it. But this is a really large, overview. Yeah. Okay, so today, if a client comes up to us, what we're doing, we understand their needs, designing a tailored workflow, right? If it's an aviation company that works to improve their pilots, experience and performance, then maybe they want to know when is the pilot stressed, right? We have a project like that. And so we're going to collect brain and peripheral physiological data, denoise it, standardize it, label it, and then provide a model which can output, how anxious is the person, how easy cognitively loaded, right? Different parameters as such. Essentially, just to understand, what we're doing is taking a whole bunch of data, right, from hundreds of thousands of people, and we're trying to kind of concentrate it into a single model, like a black box, right? And then each client can have the last centimeter for their needs, okay? So let's go over our journey with Flyte and different solutions that we used before. So the prehistoric era is where we used SSH to connect to instances to a server, right? Download data manually from S3, clone our code from Git, and run Jupyter Notebooks analyses on specific measurements. It's very limited. I don't need to expand on that. Can't do a lot of upscaling with that. And yeah, not very robust, right? In our medieval days, we had a brain site, which used Docker environment using AWS Batch. We had our own UI, which looks something like that. And we have also a programmatical launching like Flyte. We used Jupyter Notebooks only for our analysis, which were wrapped by functions that could execute them, handle their parameters, take care of their outputs, and server communication relating to execution metadata. And those workflows were quite hard-coded. We used to call the last task, and it would just call the previous tasks. We didn't have this DAG formation, directly cyclic graphs. And so then we would output an HTML and present it on the UI, similarly to what the decks are doing, right? And this one was pretty hard to scale up. It was buggy, non-flexible, and there was a lot of maintenance to do. So we need to find a solution, either to dive in deeper into our own technology or to find Flyte, right? So we upgraded our environment to a Kubernetes cluster environment, and now we can launch huge hundreds of data sets from different people, hundreds of people simultaneously. It's low maintenance. We can have SSO integration, so we can, give our clients, access to certain data that we want, and like I said, minimal maintenance, right? This is an example of one of those outputs. We had a project called the Cognitive Load project. We tried to predict the cognitive load of a person, which means how are they, overloaded? How much overload is the brain? And for example, for pilots, you can know, like, if they're highly loaded, right? Maybe they're going to make a mistake. Maybe they need to take a break and give the control to the autopilot, right? There are so many uses for this. And now you can see There are several different classical models like AdaBoost, Decision Tree, Random Forest, and XGBoost that try to predict the level of cognitive load, right? Either low or high. This is one of our first results, right? It's not the final result, but you can see the different headsets, each different measurements, right? Data sets. Each data set like that consists of a lot of data points, right? So it's not like we had, 10 or 30 data sets, data points. We had many more within each measurement, right? So this is a pretty cool usage that we had. So now I'm going to dive in a little bit. First of all, to a project I'm currently doing, and then show you some of our workflows, okay? So just to be clear, okay, so we have this main, we have this, okay. We have this main workflow, right? In this workflow, in this project, what we're doing is we are trying to extract the different frequencies of the brain signal, right? The brain waves, if you know it, alpha, beta, gamma, different frequency bands. And so if we have, for example, 2 minutes of data, right? We can take those whole 2 minutes of data. And those of you who, played with the signal processing, right? You can use the Fourier transform and get the different frequencies and how each frequency is very prominent, right? Very strong. So if, for example, we have a certain band that is very high, then it's an indication of something. So this project is about taking, for example, a full 2 minutes, extracting the brain waves from these 2 minutes, and then comparing them to little bits of information. For example, instead of taking the whole 2 minutes, I would take 1 second segments and try to extract the brain frequencies from each segment, and then average them and see how well is it compared to the whole 2 minutes. I'm not going to dive into the technical issues, but what we're doing essentially is a comparison, a correlation of different methods, different parameterizations. It's a hyperparameter optimization workflow that essentially is trying to give us what's the best method of extracting brainwaves for short amounts of data, okay? So here you have different parameters that are used for the optimizations. We have groups of parameters, which are classes of their own, which just makes it a little bit easier. Yeah, so what we're having here is a dynamic workflow, okay? Which, this is a very naive implementation for them, but we, don't really care about the performance on this one. So what it does essentially, it calls for each combination of parameters. It calls the brain frequency extractor, right? And it compares the 2 minutes with the average of the small segments that add up to the 2 minutes. So each combination calls this function, which then takes the results, takes the parameters, and outputs them, the parameters of each iteration, the differences, the correlation, the actual power spectrum, which is the brain frequencies, for the epochs, which is the small segments, and the period, which is the whole 2 minutes, right? Within this one, you also have a few layers of workflows, okay? We have, we can use 100 data sets for that. For this project, I used 10 data sets, right? 10 measurements, and with different parameters. So it added up to something like 500 tasks that can run parallelly. This is, pretty heavy stuff. So the power spectrum, the brain frequencies are extracted from both types of, segments, and the difference is calculated, the correlation. Then there is a reducing task, which just averages all the different data sets, the results, and outputs them, right? Just to see, we're gonna have another layer, right? The little segments, to get the data itself from S3, Amazon. Then we're going to pre-process it. We're going to clean it of artifacts, of different noises, and get all the movements, everything that destroys the data. We're going to really apply some game to that and make it good. Then we're going to apply another cleaning after segmenting, after splitting it to 1 second bins, for example. We're going to eliminate different channels which are too noisy to clean, right? We have 115 channels per headset. Okay, so after that, we're going to calculate the actual power spectrum, the brain frequencies, which is, there are different methods to do it. Short time Fourier transform, the Welsh method, wavelet method, yeah. And then we're going to pour it into our own data class, okay? This is something I just wanted to say. It's quite nice. This is an object that we're using, a data class, which encompasses our data, the head measurement, the actual brain data inside as a structured data set, right? Flyte's instance, Flyte's class. And then we have different metadata inside. We have the metadata inside. You can have the sample ID, the different sensor mappings, the sampling frequency, the measurement ID. Okay, so this is what we pass from task to task, and then we can choose when to the appropriate moment to download the data and open it, essentially. Okay, so this was a in-depth code review. You can see just a general look at the different directories that we have. We're getting the data from somewhere. We're using the denoising. We have different experiments, different workflows. So it's very diverse. And we have, several researchers working on different projects on the same actual code. So let's dive into several workflows that we have. We have this one experiment where we show people frogs, okay? Just an animation of a frog. It would be a green frog, then a green frog, then a green frog, then suddenly it would be a blue frog. And the subject is instructed to press the space key when he sees a blue frog. So when the subject is surprised, there is an actual brain reaction to the surprise. And we can see that. You can see this is 0, the time that the actual stimulus was presented to the subject. And then for the next 600 milliseconds, this is how his brain behaved on the different channels. Okay, here you see the 115 channels distributed on top of the head. Okay, now we have 2 groups here. Okay, each group, the average ERP, the evoked response potential, the brain reaction is averaged, and then it's compared. You can see the difference between the 2 groups. Here it's distributed per channel. Here you can see the spatial distribution, and here is a more raw look on the group as data. And here, the second group. So there are some differences, if you can, take a look, some differences. Here you see the brain reaction, through time, After 130 milliseconds, you can see this area of the brain, the back area, is used. We use Altair for the visualization, which is pretty nice and interactive. And just a UI overview of that. We use map tasks. We use the map tasks for different measurements, and we parallelize them. Different cleaning steps. The ICA, it cleans the data. ASR, it's an algorithm that cleans the data. Discarding of channels. Every single thing here is important. And then the ERP metrics, how good is the brain reaction? It is measured, and then there is a comparison here in the end. Okay, so this is one use case that we're using it. Another use case is the signal quality. The signal quality is something that we have our own algorithm that calculates how good is the signal? Is it too noisy? Is it worth using this measurement specifically? So you can see the different electrodes and the actual signal quality. Here we had a problem back in the day where this area of the head had a hard time, being stuck, the vertex. So we saw that the signal quality was not as good here. And we made some modifications, then it improved. Okay, so just a quick overview of that would be to get the data, do some pre-processing on the data, calculate the signal quality, and then actually we have also a dashboard that takes this signal quality. This one is done with Redash. Can't recommend this one, the platform, but we used it. So different dates and how good was the signal quality over different categories, different headsets, different subjects, places, So essentially we use Flyte to pour all this signal quality data into a database, timescale database, and we are retrieving this data in the dashboard. This is part of my project that I showed you, was to see how good are different parameters for the difference between the whole period, the brain frequencies, and the average of small segments of frequencies. So you can see, for example, should I mask the data? Should I clean it in a certain step? It did not affect very much the difference. Over here, you can see the second per segment. If we take larger segments and average them, it's a better, a smaller difference, right? Here, another parameter, the amount of number of FFTs. It's a technical thing. So pretty nice, right? Here you can see the different, it's the dynamic task I showed you before, running different parameter combinations. And then within each one, there is a map task that parallels different measurements. Okay. So here is a model that we developed, the cognitive load model. Okay. It extracts brain frequencies and some features from these brain frequencies. This is the group spectral features workflow, which uses map task. We generate the labels. We restructure the features for a classical model. Then we use a map task to evaluate the model in folds, okay? Which then we create an evaluation report, which is this Flyte deck that we can see over here. So this is only random forest, the different data sets, and you can see the accuracy, which is pretty nice. Almost last will be a couple minutes more. This is a workflow that extracts also brain frequencies, which is our essential unit of work. And it loads them inside a database using this dynamic workflow, and then poured into a database, which we then get data from. This is Streamlit, if you know it. This is a highly recommended platform. I would love Flyte and Union to integrate with this this platform. It allows for local data analysis and also our own domain of it. I can choose different groups and see their power spectrum, their brain frequencies, and compare them. This one you can see is pretty noisy. So this is really nice. That's pretty much it, guys. I thank you very much. And any questions, I would love to answer.
Hey, thanks, Tom. That was awesome. I don't see questions yet regarding exactly the content. So that was super interesting, and yeah, sad that we are running a bit out of time. But thank you, Tom. It was super interesting.
Thank you, guys, for having me.
Awesome. All right, for the second half of the meeting, I'll introduce stage to no other than Niels Bantilan. He is the chief ML engineer at Union. And also with us today is Haytham, chief technology officers at Union. And finally, someone who I don't know if it needs an introduction, but no other than Kelsey Hightower. So welcome, folks.
Oh, welcome.
Hello.
I'm guessing it's around 9:30 my time, and I think people are probably here. Great presentation beforehand. I've been tweeting the last couple of days about, end-to-end ML ops. I've been spending a lot of time with the team. What does this look like in production? What does it look like when a data scientist or someone doing ML goes from like their laptop or that special server you got in the corner? And you really want to bring kind of a production mindset to this, right? Like the idea that when you're training these models and you're going to actually use them in production, it would be nice if you had a workflow that was repeatable by other people on the team. And so with that, we're going to have Niels kick through and go end to end on Union's serverless offering, which was announced a couple of days ago, so recently. So we're going to see a lot of new stuff today. I'm going to hand it over to you, Niels. Welcome to the stage.
Thanks, Kelsey. Yeah, hey everyone, I'm Niels Bantilan, and I'm the chief ML engineer at Union. I've been doing applied ML for some time now, and today I want to show you a product that we built that will enable you, as Kelsey mentioned, to ship and iterate quickly on AI and ML products. So first I want to level set with you here. AI, and I'll say AI is a superset of ML and all the software systems around it to make it work well for products. It involves three things. It involves a model, a data set, and compute. You can think of a model in programming terms as a compiler. It is the algorithm that outputs a program that's learned from data. You can think of data as code. It is literally the thing that specifies the behavior of the program. The process of learning from this data is called model training. But to do this model training, you need compute infrastructure to compile these programs. And sometimes, like in the case of deep learning, you need GPUs to train models. I think we are out of the regime where you can just train a model on your laptop, although in many cases, this is still true today. There are a lot of categories of models for which you will need some kind of heavier firepower to compile these models. A case in point are language models. And this is a type of deep learning model. And at its most basic level, language models are trained to predict the next token. You can think of tokens as just words or pieces of words. So if I tell you right now, the cat sat on the blank, your mind is already doing next token prediction. I mean, obviously your mind is doing a lot of other things, but you can predict mat, table, human head. Cats can sit in a lot of different places, or any number of other plausible next words. But how do we actually customize and train these things? Instead of using something like ChatGPT or Gemini, there's many cases in which, as an organization, as a business, or maybe even as an individual researcher or product builder, I just wanted to have some different set of behavior. Well, today I'm going to show you how to train language models in a way that's repeatable and reproducible. This webinar is all about using Ollama to get started with LMs locally. And then I'm going to show you actually how to use Union Serverless, this new product we're launching, to fine-tune these models to customize their behavior. So to do this, let's start by playing around with the model. And one of the best ways that I found to do this is to interact with one locally on your computer. And luckily, the technology is maturing and a lot of tools are coming out. So today I've picked Microsoft's Phi 3 model. This was shipped a few months ago. And this is actually a model that's on the smaller end of the spectrum at a measly 3 billion parameters. To give you a sense of scale, GPT-4 is estimated to have about 1.7 trillion parameters. These circles are not exactly to scale, but it gives you a sense of how GPT-4 is roughly 3 orders of magnitude larger than Phi 3. But as you'll see, Phi 3 is being touted as an interesting model to run at the edge on a laptop, perhaps on a phone, to do certain use cases. So to get Phi 3 onto my laptop, I'm going to use Ollama. Ollama is this really cool open source project. It lets you get started with language models locally, easily. They also have kind of the serving utilities, so you can serve it on some cloud infrastructure. So you just have to install it and then invoke Ollama run, model name, in this case, Phi 3. So without further ado, it is demo time. And I'm going to get started here running Ollama on my laptop. So I've just booted up Ollama. Let me just maximize this. And one known problem about language models is they have a knowledge cutoff. And these models are typically also trained with reinforcement learning through human feedback to avoid answering questions about things beyond their knowledge cutoff, in addition to other things like sensitive topics, things that the system builders have deemed topics that are kind of out of scope for the model. So I'm going to illustrate this with a very simple example. I'm going to ask, what are the latest top news headlines in science? And it's going to generate a bunch of tokens. If we look at the top here, it's going to stop at some point, hopefully. OK, well, yeah. If you look at the top here, you already see it has been prompted. It has been trained to say, what its knowledge cutoff is. And these are some of the headlines it knows about. These may be hallucinated. We'll probably have to check and double check whether these are actually true headlines. So how do we get around this knowledge cutoff issue? Today, there are about 2 ways of doing this. One is retrieval augmented generation, or RAG. This is where you add more context to the language model's context window. And this additional data is generally from an external source. You'll need to build a software system that uses probably a vector store, retrieve some documents, and stitch together a system that's able to supplement the context window. So what I mean by this is I asked it this, right? Context window basically means I'm going to add a bunch of information before my actual question to basically feed it tokens that are up to date. So that's RAG in a nutshell. The second approach is fine-tuning. And this approach is generally a little heavier weight. You're going to need infrastructure. And so this is what I'm going to show you today. But this approach basically allows you to directly update the weights of a pre-trained model to have it learn more about a particular domain. Now, each approach, as I've alluded to, has its pros and cons. But since we're here today talking about training models and using GPUs and compute infrastructure to do these things, I'm going to show you how to fine-tune the Phi-3 language model to give it more up-to-date information about the news. But first, to do this, we're going to need a data set. So what I've done today is I have pulled data from the News API. This is a cool website that allows you to basically make requests to its API with certain query parameters, and it gives you a nicely formatted JSON response with the latest news, latest headlines, things like this. So this is going to be our data set. I've prepared this for you already here locally. And if things are a little abstract in terms of like, okay, how do I prepare a fine-tuning data set? This at its simplest form is literally what it looks like. It is a collection of documents or a corpus of documents. And here's an example, say, of the science headlines that I've created. So let me actually switch over to my editor so we can take a look at these things. I'm going to go to data, I'm going to go to science. So as you can see here, this is a basic naive implementation of a data set that basically reduces to the next token prediction task. And I formatted the template in a way that Phi-3 can understand. The first segment is basically the system message. I'm fine-tuning it to basically say, hey, you are news reporting AI that reports on the latest headlines. I give it an example of what a user query could be that maps onto the actual headlines. And then the last section is just a bullet point list of the headlines, basically the title, the publisher, the date, and the headline description. So in the real world, this would be a lot more complicated to put together. You would actually want variations in the kinds of questions you give it. So not just like a single type of question, but you get the idea, right? Again, the data set is the program that specifies the behavior that the model is meant to learn. Okay, so we have this data set, but how do I actually train it, right? I can't on my laptop do this. My laptop's going to explode. So what I'm going to do is I need a GPU. And right now, you probably see in the news, NVIDIA is, super hot right now. And I guess it has been hot, but there's a lot of demand for GPUs. And normally I would go to a cloud provider like AWS or GCP, provision a GPU instance, SSH into it, or get my hands on a GPU through Google Colab or some kind of other service that allows me to quickly spin up a GPU. Now, once I have my hands on one, I might struggle to then install all the correct dependencies if I didn't pin my package versions. But assuming I have everything right, I can just run my workload on that machine on the cloud. But there's still a problem. The thing is, I don't just want a GPU. I want my fine-tuning pipeline to run reliably every day so that the model contains up-to-date knowledge about the news headlines. So this set of problems is what Union Serverless is all about. It's about getting you a slice of that GPU supply, in addition to any other CPU compute resources you might need for your pipelines, while iterating quickly with production-grade tools. So what does this tool look like? Well, I'm going to turn your attention to my editor here. And Union is built on top of the foundation of Flyte. Flyte is an open source orchestration tool tailored towards machine learning and AI. And Union basically extends this with additional functionality. And so what I'm showing here is basically you can define your pipelines in your AI build process as code. If you're familiar with CI/CD, before I entered the tech space after CI/CD existed, so I don't know what it was before that. But we can basically break down each of the steps in the AI ML build process into code. So just stepping through this workflow I have here, this is a Flyte workflow. It takes in some inputs, and as you can see, things are strongly typed. This is an opinion that we have about building pipelines that are production grade. The first step, we're just going to create a data set. And this data set task is defined here. And all we're doing is we are calling an underlying function here. And I don't want to bog you down to the details, but this basically just calls that news API website service that I showed you earlier. I can define secrets. So I can define secrets here for the API key. I don't need GPUs for this step, so I'm just going to ask for one CPU. And I'm going to ask to generate some interesting metadata here in terms of a Flyte deck, which I'll show you later. This gives me the ability to visualize anything that's happening inside of my tasks. So the next step in the workflow is to train the model. Again, this is defined in code. What this is doing is it's calling an underlying function that uses Hugging Face transformers. This is a very common tool in the ML ecosystem. And I'm just feeding it the data set that we created in the first step, some configuration, and that's the training step. But we're not done here. We are going to then convert our model into GGUF binary format. This is a format that's, it's I think a fairly new binary format for tensor-based models, and it's just a way to serialize models in a way that's a little more compact. So you can do cool things like quantize the models, make them take up less memory. And once we've done this, we're then going to publish both the original model and the GGUF format model onto Hugging Face Hub. This Hugging Face Hub is a cool platform that allows you to share. I'll actually show you a little bit later, but it's a platform where you can share models and data sets. So we're going to share our fine-tuned model on Hugging Face Hub. So now that we have everything in place, let us get started. So I'm going to hop over to my terminal over here, and I'm going to simply run this command line command, Union.ai run. I'm going to say copy all so that I'm going to ship all of this code up into serverless. I'm going to run it on the remote serverless platform. And I'm basically going to point it to the news workflow that we've been looking at on the right-hand side. So I'm going to point it to the train workflow. And I'm going to pass in, as you can see up top here, there's a config. There are a bunch of inputs. Union.ai run will actually parse all these inputs as command line inputs. So I'm going to pass in some configuration. And finally, I'm going to pass in the categories of news headlines that I want to train on. So I'm going to say science, technology, and business. And let's run this. Uh-oh. Okay, something's up here. So let me actually just use this. Yeah, I think I had a typo in there somewhere. Okay, so what's happening here is, as you can see, you can read here that Union is actually building images for us. And I know Docker isn't everyone's cup of tea. So we've taken a lot of care for Union to handle building container images for you. Once the image building is done, it's cached. So these actually were pre-built, and so that's why they completed very quickly. But with Union and Flyte, we actually have abstracted Docker files and container file definitions. So if we look at our tasks here on the right-hand side, we see that we have an image spec definition here. And what this does is it actually allows you to not worry about making Docker files and building those Docker images. So image spec is a high-level SDK that allows you to just specify your requirements. And if you have pre-built images, it'll just reuse those. And additionally, if you just have a pre-built image that you've built kind of outside of the Flyte and the Union set of opinions, you can, provide your fully qualified container URI here as a string. So we give you a lot of options, but we make it super easy for folks who are not maybe super familiar with infrastructure work and Docker to get started really quickly. So now that our training job is kicked off, let me show you the Union UI. So as you can see here, we've already kicked off the training model job, and a lot of steps are already cached. And this is one thing that I think is super powerful about Flyte and Union Serverless. If we look at the graph view here, let me just expand my screen. We can see the shape of the directed acyclic graph here, from the dataset creation step to the model training step to the serialization step to the publishing step. And because models can take a long time to run, I've pre-run this model and the dataset creation step so that we don't have to sit around here waiting. Now, we can look at the source execution that this particular execution is used to just quickly finish our pipeline. So here is the original execution. You can see a failed step over here. We can debug that later. But one cool thing I want to show off here is we can view the utilization of our training step. And so this is kind of the MLOps portion of this entire platform, which is I can see what my memory utilization, CPU, GPU memory allocated, GPU utilization over time. And this allows me to actually calibrate and iterate on my workflow so that I can maximally utilize the resources that I've set for myself. As I can see here, I'm only using about, let's say, on average, 50% of my GPU memory that's available. And this is a signal to me that maybe I can increase my batch size, maybe I can increase my model. I can use a larger model here. But this gives me insights into what's going on, not only at the graph level, but at each node in this DAG, I can see what the utilization was and debug each step as it succeeds or it fails. We can also hop onto the weights and biases dashboard. So this is something, if I hop back onto my terminal, in the training task, we're actually using weights and biases. So this integrates really nicely with existing ML tools. But just to call out certain things in this training task, I'm actually requesting for a T4 GPU accelerator, I'm asking for 1 GPU, 24 gigs of memory, 4 CPUs. I'm specifying my Hugging Face API and weights and biases API here, secret. And in the task code, I'm doing a bunch of stuff, including setting various parameters to use weights and biases. All right. So now, at the end of my pipeline, I can look at the outputs over here. And I've formatted them nicely so that it's kind of human readable. This is the Hugging Face GGUF model file. This is actually stored on S3. So everything is stored and handled for you in Blob Store by Union. And here's the repo URL for the GGUF model that we've just published. So here it is. I can probably stand to make the README a little bit better here for the model card. But if we look into files and versions, we can see we have a model.gguf file here. And this is the file we're going to download directly into our CLI and rerun our fine-tuned model. But actually, before I get to that, I did want to call back to the dataset creation step. So this is the pipeline that just ran. And we can look at the source execution of the create dataset step. And here's the original execution that produced it. Recall that I mentioned that I had the dataset creation task create a flight deck for me. And what this does actually is it gives me arbitrary reporting and insights into what's happening in my task. So a bunch of these tabs basically just ship by default. So this actually gives you a profiling into what, how long each step in the task took. So our user code took just a short percentage of the overall task time. But we can see here, these are the dataset examples that I've given it, just literally 3 examples. Here's the science one that you might remember from earlier, but with updated dates here for basically today, June 11th, 2024. So this is basically the program that maps the system and user message onto our new updated headlines for each of these news categories. So in the last part of this demo, I really want to show you, to bring it full circle, and I'm going to take you back to the CLI. And what I'm going to do is I'm going to make sure I get these commands right. And I'm going to download, using the Hugging Face CLI, the model.gguf file that we just created. So this is going to take a few seconds, but while this is working, I want to call out a very cool, I think, OLAMA feature here, which is the model file. This is something that, when I saw it, I kind of fell in love with it. It's a very cool idea where, if you look at this, it kind of looks like a Docker file. Or if you don't use Docker, it's kind of a declarative way to specify the behavior and the definition of a model. So in the top here, we're going to point it to the local directory where I'm actually downloading this here right now. I'm going to give it a template. So this includes the system message, the user message, and the assistant message. I've given it some stop parameters, some other things here, other parameters here to limit its prediction, number of predictions, just a random seed, so things are reproducible. And finally, the system message here that tells it is a news reporting AI. So it's going to take a few more seconds, but I think there are a lot more things you can do with these model files. But I imagine this or something like this will become kind of a de facto way to declaratively specify what model you're using, what its behavior is. You can customize the templates up here. You can customize the system behavior to have it match your model that you've just fine-tuned. So here's the local file that we saw earlier on Hugging Face Spaces. And And we're going to hop back here. And I'm going to say Olama create phi3 news, pointing it to this model file that I just showed you. It's going to do a few things here, transfer the model data. And after a few seconds, should be ready. Still baking. Awesome. And now we're ready to boot up our fine-tuned model. And I trained this a lot, or I tried this a lot, and hopefully this will work as expected. So we're going to circle back and ask the question we just asked. Okay, so gave a short answer here. We can see that it has an updated response. I'm a little skeptical about this headline. New studies suggest fossilized tails have been found on a moon launched by SpaceX. This is a weird headline. Let's try it again. Okay, this looks like more like it. So this is, this gives you a practitioner's view onto the limitations of LLMs. But this, let's actually Google this and try and verify. Okay, so this actually, I don't think, does not exist. So this, again, is just a very simple toy demo, but I hope it shows you and gives you a sense of how you can actually fine-tune these models. There's a lot more work, and actually, we're at a good position to iterate. So, for example, say I want to fine-tune my model to also give sports headlines. Well, basically, all I have to do is update this input here, rerun this exact same command, and everything will run the same way, all on the same infrastructure, modulo the new data set that we're creating with the sports headlines. So to summarize, the whole purpose of Union Serverless is to simplify ML and AI ops. And we do this by allowing you to build build processes as code, giving you tools for observability, and allowing you to increase your velocity from running locally. So I didn't show this, but you can actually run all of this code locally. You can then run it on serverless with the remote command. You can then update the data set or any other parameters. And you can scale up the model by changing the configuration using maybe the Llama 3 8 billion model. I mentioned earlier that there are two approaches, fine-tuning and RAG. I'm actually doing a RAG workshop tomorrow, building your own custom chat assistant with serverless. The QR code is here. You can check out the event on this link. And yeah, sign up on the top link over there if you want to try out serverless. If you want to contact us, there's the link in the middle. And if you want to schedule a demo, it's the link at the very bottom.
Awesome. Thank you, Niels. Oh, this was great. We got a ton of questions as you were demoing. We were trying to catch up to all of them, but I have a couple that I wanted to add that are related to what you were just demoing. So for someone who is just starting with LLM and trying to solve a problem they have, where do they start? Do they start by choosing a base model, and how do they go about doing that? There are a ton of leaderboards and benchmarks, and yeah, how do you sift through all of this?
So it depends on where you're starting. So let me try to qualify this. My recommendation is basically to use a state-of-the-art, off-the-shelf LLM via API calls. That's if your goal is to build an AI-powered product that, let's say is a customer service bot or something of this nature. Assuming you're fine sort of sending data to a third party, I would recommend any of the top lab APIs, ChatGPT or GPT-4, Anthropic's Claude, Gemini, these things, and then coupling that with retrieval augmented generation. So that's the RAG approach that I mentioned earlier. This, I think, will get you pretty far. I think the next level is if you don't want to send data, you can use an open weights model like Llama 3, Mistral. There are a bunch of these. And on any given day, there'll be changes in these leaderboards. So just pick one, on the top, whatever, 20 or 30. And again, starting with RAG is the most practical because the iteration speed is much faster. Basically, you're just kind of like squeezing a bunch of information into the model's context window, and the question basically retrieves that information. Fine tuning is probably I would reserve for very domain-specific languages, let's say biology or some special science research or something like this. And again, these are orthogonal approaches. I can fine-tune a model and then use RAG, right? Fine-tuning updates the conditional probabilities of the underlying model. So assuming you have an evaluation system in place, which is a whole other can of worms, you could use both approaches.
And I guess one last question, would using a system or like writing a workflow to try out different models help in any way or simplify that process? Or what's your take on that?
Totally. I think the hardest part about these things is typically the evaluation data, the test data, or data in general. That's typically the most labor-intensive part. But assuming you have this in place, you could use Union to basically, it's hyperparameter tuning at a certain level. You switch out the model you use, and as long as let's say it's a RAG system, as long as your RAG system doesn't have access to the test data, and you can actually ask it questions and evaluate on the test data, you can apply it on API call based models, open source models, fine-tuned models, and then you can see which one performs best for your context.
Awesome. Thank you for all of this. I think we are a little bit over time, so we'll wrap it up. But yeah, quick one more time call of action. Sign up for Union Serverless at sign up to Union.ai. And we can't wait to see what you will all build with the platform.
Yeah, I see a bunch of questions here. I'll actually try to circle back on LinkedIn, and I'll take a screenshot and see. I'll reach out to the folks who are asking stuff and answer these questions.
Perfect. Back to you, David.
All right, I think that's it. And yeah, the recording is immediately available after the live stream is finished. It will be available on both Flyte's and Union's YouTube channel. And yeah, if you have further questions around Flyte and Union, please join Flyte's Slack channel or reach out through LinkedIn if that works better for you. So thank you all for joining, and hope to see you in the next one.
All right.
Bye.
Bye.